Okay, so we've got another listener question to kick things off today.
Sounds good.
This one really gets to the heart of what makes Kubernetes so powerful. Let's hear it.
All right, let's hear what they have to
Here
say.
we go.
Okay.
Audio begins with a question.
Hmm.
So how does Kubernetes actually make sure my application stays running even if a server fails? And how does it just magically scale up when there's more traffic?
Wow, that's a great question, and it really captures the essence of why so many people are turning to Kubernetes for their modern application needs.
It does. And you know what's even better? You shared some really insightful resources that dive deep into how Kubernetes actually pulls all this off. So we're going to unpack that together today.
Yeah, we'll try to distill these complex mechanisms into something that's understandable and digestible, without getting lost in a sea of technical jargon.
Right. Because the goal here is to understand the why behind the magic so you can really appreciate the elegance of the design and how it all comes together.
Exactly. We want to demystify it a bit.
So let's start with the big picture. Kubernetes has a very modular architecture, right?
Yeah, you can break it down into two main parts. You've got the control plane, which is like the brain of the operation. It's where the decisions are made and the commands are issued. Then you have the worker nodes. These are the workhorses where your applications actually run.
Okay, so the control plane is calling the shots and the worker nodes are carrying them out.
Right. It's a pretty clever division of labor.
And a central concept here is the desired state. You tell Kubernetes exactly how you want your application to look, how many instances should be running, what resources they need, and then it works tirelessly to make that a reality.
Exactly. It's like setting a target, and Kubernetes is constantly aiming for it.
So how does it actually hit the target? How does it know what's going on and what needs to be adjusted?
Well, that's where these continuous control loops come into play. Kubernetes is always monitoring the actual state of your cluster and comparing it to the desired state. If there's a mismatch, maybe a server crashes or traffic spikes, Kubernetes automatically kicks in to correct things and bring everything back in line.
That's what we mean by self-healing and scaling.
Right, you got it. And it's all driven by these control loops that are constantly running in the background, always making sure the actual state matches what you defined as the desired state.
That's pretty impressive. Okay, so let's dive into some of the key players that make all of this happen.
Sure, let's start with the kube-apiserver. It's a pretty central piece of the puzzle.
Yeah, it sounds like the command center of the control plane.
It is. You can think of it as the conductor of an orchestra. All communication within the Kubernetes cluster goes through the kube-apiserver. Whether you're using kubectl, the command line tool, or another component needs to talk to something, or even an external system wants to interact with the cluster, everything goes through this central point of entry.
So it's like the grand central station of the Kubernetes world.
Exactly. And to make sure everything runs smoothly and securely, the kube-apiserver has this multi-stage access control process.
Like a bouncer at a club?
Haha. Yeah, kind of. But it's a very thorough bouncer with multiple layers of checks. It starts with authentication.
Which is basically proving who you are, right?
Right. You need to present the right credentials to get in. The kube-apiserver supports various authentication methods, like using client certificates, special tokens, even hooking into external authentication services.
So it's flexible enough to handle different security requirements.
Exactly. Then comes authorization.
This is about making sure you're allowed to do what you're trying to do.
Precisely. Just because you're allowed in the club doesn't mean you can access the VI2 area. The kube-apiserver uses role-based access control, or RBAC, to manage this. You define roles with specific permissions and then assign those roles to users or groups. It's like giving out different badges with different levels of access.
So RBAC is about controlling who can do what within the cluster.
Exactly. It's all about fine-grained control over permissions, making sure only the right entities have the right level of access to be what they need to do.
That makes sense. And then there's this admission control stage. What's that all about?
Admission control is another layer of security. It kicks in after authentication and authorization, but before a request actually gets processed.
Like a final sanity check.
Yeah, basically, it's a way to enforce specific policies and rules on how the cluster is used. Admission controllers can validate requests, ensuring they meet certain criteria. They can even mutate requests, modifying them before they get applied.
So they can block bad requests or even tweak them to be more aligned with the cluster's policies.
Exactly. It's a really powerful mechanism for fine-tuning how the cluster operates and making sure everything stays secure and consistent.
And you mentioned that the kube-apiserver is the only component that talks directly to etcd. What's etcd?
Etcd is the brain of the Kubernetes cluster. It's a distributed key value store where all the crucial information about the cluster is kept.
Like the configurations, the state of everything.
All of that. It's like a giant database that holds the entire state of the Kubernetes world.
And the kube-apiserver is the only one with direct access.
Right. It acts as the gatekeeper. When any component needs to read or write data, it goes through the kube-apiserver, which then interacts with etc. This ensures that the data is always consistent and secure.
So it said it is like Fort Knox for Kubernetes data.
Haha, yeah, you could say that it's highly available and reliable using this algorithm called Raft to keep the data synchronized across multiple nodes.
So even if one node fails, the data is still safe and accessible.
Exactly, and it's got this really cool feature called Watch, which allows other components to subscribe to changes in specific data.
So they can react in real time to updates.
Yeah, if something changes in etc., the components that are watching that data get notified instantly.
That's how they can automate all these responses and keep the cluster running smoothly.
Exactly. It's like a built-in notification system that allows Kubernetes to react quickly to changes.
Okay, so we have the kube-apiserver as the command center and etc. as the brain. What about actually placing applications onto those worker nodes? That sounds like the job of the kube-scheduler.
It is. The kube-scheduler is like a highly intelligent matchmaker. It takes new pods, which are the basic units of deployment in Kubernetes, and finds the best worker mode for them to run on.
It's got to consider things like available resources on each node, right?
Absolutely. It also looks at any constraints you've defined, like node selectors, taints, and tolerations, and these things called affinity and anti-affinity rules.
So you can be really specific about where you want your pods to run?
Yeah, you have a lot of control over the placement. The scheduler uses this two-step process called filtering and scoring to make its decisions.
Tell me more about that.
Okay, so in the filtering phase, the scheduler goes through all the available nodes and eliminates any that don't meet the basic requirements of the pod. Like, if the pod needs a certain amount of memory, the scheduler will filter out any nodes that don't have enough free memory.
So it narrows down the options to only the viable candidates.
Right? Then in the scoring phase, it ranks those viable nodes based on the set of criteria, like how much of the node's resources are already being used, any preferences you've expressed through those affinity rules, and things like data locality, trying to place the pod close to the data it needs to access.
So it's not just about finding a node that can run the pod. It's about finding the best node for that particular pod?
Exactly. It's all about optimizing resource utilization and ensuring your applications run as efficiently as possible.
Wow, okay, so the kube scheduler is pretty smart, but once the pods are placed, how do we make sure they keep running and scale up or down as needed? That sounds like a job for the kube-controller-manager.
You got it. The kube-controller-manager is another key player in the control plane. It runs these things called controllers, which are like automated control loops that are constantly monitoring the cluster and making sure things stay in line with the desired state.
So they're like the enforcers.
Yeah, you could say that they watch for any deviations from the desired state and then take corrective actions.
Give me some examples.
Well, you have the node controller, which keeps an eye on the health of the worker nodes. If a node goes down, the node controller will detect that and take action to reschedule any pods that were running on that node.
So it's like the first responder in case of node failures?
Exactly. Then you have controllers for deployments, replica sets, and pods. These guys make sure that the right number of replicas are running at all times, and they handle things like updates and rollbacks.
So they keep the application running smoothly even when changes are being made.
Right. They also handle scaling up or down the number of replicas based on changing demands.
So that's how Kubernetes automatically adjusts to traffic fluctuations.
You got it. And there are controllers for other things too, like managing services, endpoints, namespaces, persistent storage volumes, all sorts of stuff.
So it's like a whole army of automated specialists, each taking care of a specific aspect of the cluster.
Exactly. And they all work together seamlessly to maintain the desired state.
Okay, so we've covered the control plane. Now let's talk about what's happening on those worker nodes. What's the key component running on each of them?
That would be the kubelet. The kubelet is like the local agent for each worker node. It's responsible for managing the containers running on that node.
So it's like the on-site manager for each server.
Right. It receives instructions from the kube-apiserver in the form of pod specs. These pod specs describe what containers should be running, what images they should use, what resources they need, all that stuff.
And the kubelet makes it happen.
Exactly. It talks to the container runtime, which could be Docker or containered or something else. It tells the runtime to pull the images, start the containers, stop them, delete them, whatever needs to be done.
And it also handles those health checks we talked about before.
Right, the liveness and readiness probes. If you define those in your pod spec, the kubelet will periodically run them to make sure the containers are healthy.
So if a container is unresponsive, the kubelet will try to restart it.
Exactly, and it reports all this information back to the kube-apiserver. So the control plane always has an accurate picture of what's going on.
Okay, so the kubelet keeps things running on the individual nodes, but how does network traffic actually get routed out to the right pods, especially when you have multiple replicas of a service running across different nodes.
That's what kube-proxy comes in. Kube-proxy runs on every worker node, and it acts as both a network proxy and a load balancer.
So it's directing traffic within the cluster.
Yeah, it maintains the network rules that make sure traffic for a particular service gets sent to the right pods. It also handles service discovery so applications can communicate with each other without needing to know the IP addresses of individual pods.
So it's like the internal traffic cop and directory service all rolled into one.
Yeah, basically, it works closely with the kube-apiserver to keep track of services and endpoints. It uses either iptables or IPVS to set up the network rules.
So it's a crucial part of making the whole networking layer work seamlessly.
It is. Without kube-proxy, communication within the cluster would be a real mess.
Okay, we've covered a lot of ground here. We've got the core components and how they work together. Now let's shift gears and talk about how we manage the resources our applications need. That's where resource requests and limits come in, right?
Exactly. When you define your application, you can specify resource requests and limits for each container in your pods. These basically tell Kubernetes how much CPU and memory each container needs.
Okay, so requests are like asking for a certain amount of resources, and limits are setting a ceiling on how much they can use.
Right. The requests are used by the kube-scheduler to make sure a node has enough resources available before placing a pod there.
So if you request too much, you might not be able to find a suitable node.
Exactly. And the limits are there to prevent containers from hogging all the resources and potentially causing problems for other applications running on the same node.
They act as a safety net.
Right. They make sure things stay balanced and no single container can take over the whole machine.
And you mentioned something about quality of service classes, or QoS.
Yeah, Kubernetes uses those to categorize pods based on their resource requirements and limits. It helps to prioritize things during scheduling and also during eviction if a node starts running low on resources.
So pods with guaranteed resource allocations get treated differently than pods that are more flexible?
Exactly. It's a way to make sure that critical applications get the resources they need even when things are tight.
So let's say we've defined our application and its resource needs. How does that actually get deployed into a Kubernetes cluster?
Well, you typically start with a YAML manifest file. This file describes all the components of your application, the deployment services, any other resources you need. You submit this file to the kube-apiserver using kube-apply.
And then the magic happens.
Yeah, kind of. The API server validates the file, persists the definitions in etc., and then the various controllers kick in to make it all happen. The deployment controller creates the pods, the scheduler finds places for them to run the kubelets on the nodes, start the containers, kube-proxy sets up the networking. It's all beautifully orchestrated.
It's impressive how all these pieces work together.
It is. And during this whole process, a pod goes through a series of phases, from pending to running to succeeded or failed. It's like a life cycle that reflects the current state of the pod.
And we also briefly touched on different deployment strategies earlier. Can you remind me what those are?
Sure, you have rolling updates where new versions are gradually rolled out while old versions are scaled down. Then there are recreate deployments where all the old pods are terminated before new ones are created. And you have blue-green deployments where two identical environments are run side by side and traffic is switched over.
So you have options depending on your needs and risk tolerance.
Exactly. And finally, let's talk about scaling. We mentioned the deployment controller managing replica counts, but there are also more automated ways to scale things right.
Yeah, that's what I was getting at. How does Kubernetes handle those traffic spikes and make sure my application can handle the load?
Well, there's the horizontal pod autoscaler, or HPA, which automatically scales the number of pods based on observed metrics, like CPU usage or custom application metrics.
So if CPU usage goes up, the HPA will spin up more pods to handle the load.
Exactly. And there's also the vertical pod autoscaler, or VPA, which can adjust the resource requests and limits of individual pods based on their actual usage.
So it can give a pod more resources if it needs them?
Right. And at the cluster level, you have the cluster autoscaler, which can add or remove worker nodes to meet the overall resource demands of the cluster.
So Kubernetes can scale itself up or down as needed.
Exactly. It's all designed to be very dynamic and responsive to changing conditions.
Wow. Okay, so we've covered a lot of ground here. We've really gotten into the nitty-gritty of how Kubernetes works. It's an amazing system.
It is. And what's truly remarkable is how elegantly all these different components come together to create this self-healing, self-scaling platform.
It really is a testament to good design.
Absolutely. So what do you think? Has this demystified Kubernetes a bit for you?
Absolutely. I think we've gone from a basic understanding to a much deeper appreciation for how it all works, and I hope our listeners feel the same way.
Yeah, hopefully this gives them a solid foundation for working with Kubernetes and maybe even sparks some ideas for how to leverage these concepts in their own applications.
That's what we're all about here, inspiring people to think differently about how they build and deploy their software.
So, to our listeners out there, what are your biggest takeaways from this deep dive? What aspects of Kubernetes are you most curious about? We'd love to hear your thoughts.
And if you have any other topics you'd like us to unpack, let us know. We're always up for a challenge.
So, until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with technology.
See you in the next deep dive.